universe stretches before us in every direction. A vast cosmic tapestry woven from light and darkness, matter and mystery. Tonight, we embark on a journey to explore one of the most profound questions humanity has ever asked. Is there an edge to the universe? Does our cosmic home have boundaries, walls, or limits of any kind? Or does it extend forever? An infinite expanse that defies our very ability to comprehend it. This question has haunted philosophers, scientists, and dreamers for thousands of years. Ancient civilizations gazed up at the night sky and wondered what lay beyond the stars. Medieval scholars debated whether the heavens had walls or continued endlessly into realms unknown. And today, modern cosmologists, armed with powerful telescopes and sophisticated mathematics, continue to grapple with this same fundamental mystery. Let us begin our exploration with something remarkable that many people have never considered. When we look up at the night sky, we are not seeing the universe as it exists right now. We are looking back in time. The light from distant stars and galaxies takes years, centuries, or even billions of years to reach our eyes. This means that every time we gaze at the cosmos, we are witnessing history unfolding across incomprehensible distances. The light from our nearest stellar neighbor, Proxima Centauri, left that star over 4 years ago before it reached Earth. When we observe the Andromeda galaxy, our closest large galactic neighbor, we see it as it appeared roughly 2.5 million years ago. Early humans were just beginning to walk upright on the African savanna when that light began its journey toward us. This delay in light travel creates something scientists call the observable universe. The observable universe represents the portion of the cosmos that we can theoretically see from Earth. It has a boundary, but that boundary is not a physical edge or wall. Instead, it is a horizon created by the finite speed of light and the finite age of the universe. Current scientific understanding suggests that the universe is approximately 13.8 billion years old. This means that light has had only 13.8 billion years to travel through space and reach us. Any light that originated from beyond a certain distance simply has not had enough time to make the journey to Earth. The boundary of the observable universe marks this cosmic horizon beyond which we cannot see. The observable universe spans roughly 93 billion light-years across. You might wonder how this can be possible if the universe is only 13.8 billion years old. Surely light could only have traveled 13.8 billion light-years in that time. The answer lies in one of the most extraordinary discoveries of modern cosmology. The universe itself is expanding. Space is not static. It is constantly growing, stretching like the surface of an inflating balloon. Galaxies are not moving through space away from us. Rather, the space between galaxies is expanding, carrying them along for the ride. This expansion means that the most distant light we can see has traveled much farther than its age might suggest, because space itself has been stretching behind it throughout its journey. This brings us to a crucial distinction that many people find confusing. The observable universe and the actual universe are not the same thing. The observable universe is the portion we can see. The actual universe may be far, far larger. In fact, many cosmologists believe the actual universe extends well beyond our observational horizon. Perhaps infinitely so. There is a peculiar phenomenon that occurs at the very edge of our observable universe, something that challenges our intuitions about space and time. The most distant objects we can observe are moving away from us so quickly due to the expansion of space that they are now receding faster than the speed of light. This seems impossible. Nothing can travel through space faster than light. But these distant galaxies are not traveling through space. Space itself is expanding, carrying them away at speeds that exceed light. This means that light leaving those distant galaxies today will never reach us. They have crossed a boundary called the cosmic event horizon. We can still see the ancient light they emitted billions of years ago, but their current state is forever hidden from us. They have effectively left our accessible universe, moving into a realm we can never observe or interact with again. Now, let us delve into something even more mysterious. What lies beyond the observable universe? Scientists cannot answer this question with certainty, because by definition, we cannot observe what lies beyond our cosmic horizon. However, there are compelling theoretical reasons to believe that space continues far beyond what we can see. The geometry of the universe provides important clues. Scientists have measured the universe and found it to be remarkably flat. In cosmological terms, this means that the angles of a giant cosmic triangle add up to exactly 180 degrees, just as they would on a flat piece of paper. If the universe were curved like the surface of a sphere, these angles would add up to more than 180 degrees. If it were curved like a saddle, they would add up to less. The flatness of the universe has profound implications for its overall size and shape. A perfectly flat universe could theoretically extend infinitely in all directions. There would be no edge, no boundary, no wall where space simply ends. You could travel in a straight line forever and never encounter a limit. However, there is another possibility. The universe could be flat but finite, wrapped around itself in higher dimensions that we cannot perceive. Imagine an ant crawling on the surface of a sphere. The ant perceives its world as two-dimensional and flat. It could crawl forever without encountering an edge, eventually returning to its starting point. The surface of the sphere is finite in area, but has no boundaries. Similarly, our three-dimensional universe could be wrapped around in a higher fourth spatial dimension. Light, traveling in a straight line, might eventually circumnavigate the entire cosmos and return to its starting point. In such a universe, if you could see far enough, you would eventually see the back of your own head. You would observe the same galaxies repeated in every direction, like images in a hall of mirrors. Scientists have searched for evidence of this cosmic wrapping. If the universe were finite and looped back on itself, we might see the same patterns of galaxies repeated at different distances. We might find matching circles in the cosmic microwave background radiation. So far, no such evidence has been found. This suggests that if the universe does wrap around, it does so on scales larger than we can observe. Let us now consider what it would mean for the universe to have an actual edge. What would such an edge look like? What would happen if you reached it? These questions reveal fundamental problems with the concept of a cosmic boundary. If the universe had a wall or edge, what would lie on the other side? Saying that nothing lies beyond the edge creates a logical problem. Nothing is still something. It is empty space, and empty space is part of the universe. So if there is empty space beyond the supposed edge, then the edge was not really the end of the universe. Some might suggest that the laws of physics simply break down at the edge, that space and time cease to exist. But this creates its own problems. If space does not exist beyond the edge, then the edge itself has no location. It cannot be somewhere if there is no space for it to occupy. The very concept of an edge requires space on both sides to define it. This logical puzzle has led most cosmologists to conclude that the universe either extends infinitely or wraps around on itself. Both options avoid the problem of having an actual edge. Both options mean that no matter how far you travel, you will never reach a wall where the cosmos simply stops. There is another fascinating aspect of cosmic geometry that few people have encountered. The shape of the universe might be far stranger than simple flatness or curvature. Some theoretical models suggest the universe could have a shape called a three-torus, a higher dimensional donut that connects back to itself in complex ways. Others propose even more exotic topologies, with multiple connections and strange loops. Imagine a universe shaped like a video game screen, where exiting the left side causes you to reappear on the right, and exiting the top brings you back at the bottom. Now extend this concept to 3 dimensions, with connections in every direction. Such a universe would be finite in volume, but without edges. You could explore forever without reaching a limit, constantly returning to regions of space you had visited before. The Poincaré dodecahedral space model proposes something even stranger. In this theoretical shape, the universe would be finite with a volume roughly 80 times the observable universe, but it would have the topology of a 12-sided geometric figure, connected in complex ways. Light would take multiple paths through such a universe, and we might see multiple images of the same cosmic structures from different angles. Scientists continue to test these exotic possibilities against observations of the cosmic microwave background and the distribution of galaxies. So far, the evidence favors a simple, flat universe, but the door remains open to stranger geometries, lurking just beyond our observational reach. Now let us explore the cosmic microwave background radiation, the oldest light in the universe, and our most important tool for understanding cosmic structure. This faint glow permeates all of space, a remnant of the universe's earliest moments that carries secrets about its shape, size, and ultimate fate. Approximately 380,000 years after the Big Bang, the universe cooled enough for atoms to form. Before this moment, space was filled with a hot plasma of particles and radiation, opaque to light like a dense fog. When atoms formed, the fog cleared, and light was free to travel through space unimpeded. That light has been traveling ever since, cooling and stretching as the universe expanded. Until today, it reaches us as a faint microwave glow, with a temperature of just 2.7 degrees above absolute zero. The cosmic microwave background is remarkably uniform in all directions, with temperature variations of only about 1 part in 100,000. This uniformity tells us something profound about the early universe. At some point, all regions of what would become our observable universe were in thermal contact, able to exchange energy and reach equilibrium. This seems impossible given the vast distances involved, unless space itself expanded faster than light in the earliest moments of cosmic history. This period of exponential expansion, called cosmic inflation, may have occurred in the first tiny fraction of a second after the Big Bang. During inflation, the universe expanded by a factor of at least 10 to the 26th power, doubling in size roughly every 10 to the minus 37 seconds. Regions of space that started in contact were flung apart so rapidly that they now lie beyond each other's observable horizons. Inflation has profound implications for the question of cosmic edges. If inflation occurred, the actual universe could be unimaginably larger than the observable universe. Some calculations suggest the total universe might be at least 10 to the 23rd power, times larger than what we can see. Others propose it could be infinitely large, with our observable universe representing just an infinitesimally small patch of a boundless cosmic fabric. The tiny temperature fluctuations in the cosmic microwave background are equally fascinating. These variations, mapped in exquisite detail by satellites like the Wilkinson Microwave Anisotropy Probe and the Planck Space Observatory, represent the seeds of all cosmic structure. Regions of slightly higher density in the early universe attracted more matter through gravity, eventually growing into the galaxies, galaxy clusters, and cosmic filaments we observe today. The pattern of these fluctuations also contains information about the geometry of the universe. Scientists can use the characteristic sizes of hot and cold spots in the cosmic microwave background to measure the curvature of space. These measurements consistently show the universe to be flat to within 1% accuracy, supporting the idea of an infinite or vastly extended cosmos without edges. Let us now turn our attention to an even more mysterious aspect of the universe: the nature of dark energy and its implications for cosmic boundaries. Dark energy is the name scientists give to whatever is causing the expansion of the universe to accelerate. Discovered in 1998 by two independent teams of astronomers studying distant supernovae, dark energy remains one of the greatest mysteries in physics. The universe is not only expanding, but expanding faster and faster with each passing moment. Galaxies are racing away from us with increasing velocity. The space between cosmic structures is stretching at an ever-quickening rate. In the far future, this acceleration will isolate our local group of galaxies, making distant galaxies invisible as they cross beyond our cosmic horizon. Dark energy appears to permeate all of space uniformly. It does not clump or cluster like ordinary matter or even dark matter. Instead, it exists everywhere with the same density, a constant energy of empty space itself. As the universe expands and more space is created, more dark energy comes into existence, driving further expansion in a runaway process. The nature of dark energy remains unknown. The leading explanation is that it represents the energy of the quantum vacuum, the bubbling sea of virtual particles that briefly pop into and out of existence throughout all of space. However, calculations of this vacuum energy produce values that differ from observations by about 120 orders of magnitude, possibly the largest discrepancy between theory and observation in the history of science. Some scientists propose that dark energy is a dynamic field called quintessence, changing over time and space in ways we have not yet detected. Others suggest it could be evidence that our understanding of gravity on cosmic scales is fundamentally flawed. Perhaps general relativity, which has passed every test at smaller scales, requires modification when applied to the universe as a whole. What does dark energy mean for the edge of the universe? If dark energy continues to accelerate expansion forever, the observable universe will gradually shrink. Galaxies that we can see today will eventually cross our cosmic horizon and disappear from view. In the far future, only our local group of galaxies will remain visible, everything else having been carried away by the expansion of space. This fate is called the Big Freeze or heat death. Over unimaginable timescales, the universe will become increasingly cold, dark, and empty. Stars will burn out. Black holes will evaporate. Even matter itself may decay into radiation. The universe will approach a state of maximum entropy, a uniform sea of photons at temperatures approaching absolute zero. In such a scenario, the observable universe becomes ever smaller, while the actual universe may continue to expand forever. There is no edge, only an ever-receding horizon, beyond which information can never flow. The cosmos becomes an infinite expanse of nothingness, each region isolated from every other by the relentless expansion of space. Now let us explore a different possibility, one that suggests the universe might be much stranger than simple, infinite expansion. Some theoretical physicists propose that our universe could be just one bubble in an infinite foam of universes, a concept known as the multiverse. The idea of the multiverse arises naturally from certain interpretations of cosmic inflation. If inflation occurred in our cosmic past, it might be happening eternally in other regions of space. Different patches of inflating space could spawn different universe bubbles, each with potentially different physical laws and constants. Our universe would be just one island in an infinite archipelago of cosmic domains. In this picture, our universe does have an edge of sorts, a boundary where our bubble meets the inflating void or neighboring bubbles. However, this edge would not be like a wall we could approach and touch. It would be expanding away from us faster than light, forever unreachable. And beyond it would lie not nothing, but other regions with their own properties and histories. Some versions of the multiverse theory suggest an even more radical picture. In the many worlds interpretation of quantum mechanics, every quantum event that could go multiple ways does go multiple ways, creating branching universes for each possibility. In such a scenario, the multiverse would contain infinite copies of you, each having made different choices and experienced different outcomes. The multiverse remains highly speculative. By its very nature, other universe bubbles would be unobservable from within our own. Critics argue that a theory which cannot be tested is not truly scientific. Supporters counter that the multiverse emerges naturally from well-established physics and may eventually yield testable predictions. If the multiverse exists, the question of whether our universe has an edge becomes both simpler and more complex. Our particular cosmic bubble might indeed have a boundary, but that boundary would separate us from an even larger reality. The edge of our universe would not be the edge of existence, just the edge of our particular island in an infinite cosmic sea. Let us now journey into the realm of speculation and consider what some of the most creative minds have imagined about cosmic boundaries. These ideas may not be proven science, but they stretch our imagination and challenge our assumptions about the nature of reality. Some philosophers have suggested that the universe might be finite in a very different sense, not in space, but in information. Perhaps there is a maximum amount of information that can exist, and the universe is simply the physical manifestation of that information limit. In such a picture, the edge of the universe would be where information runs out, a boundary defined not by walls, but by the fundamental limits of what can be known or described. Others have proposed that our three-dimensional universe exists on the boundary of a higher dimensional space, much like a hologram encodes three-dimensional information on a two-dimensional surface. In this holographic principle, derived from studies of black holes and string theory, the universe might be a projection from a lower dimensional boundary. The edge of our reality would be the surface from which our entire existence is projected. The simulation hypothesis takes this idea even further. If advanced civilizations can create simulated universes indistinguishable from reality, and if such simulations are common, then we might be more likely to be living in a simulation than in base reality. In such a case, the edge of the universe would be wherever the simulation ends, limited by the computational resources of our cosmic programmers. These speculative ideas, while fascinating, remain outside the realm of testable science. They serve more as philosophical thought experiments than scientific theories, yet they remind us that the question of cosmic edges touches on the deepest mysteries of existence, matters that may forever exceed our ability to answer with certainty. Let us now return to firmer ground and explore how astronomers actually measure the universe. Understanding these methods helps us appreciate both what we know and the limits of our knowledge about cosmic structure and boundaries. The cosmic distance ladder is a series of techniques astronomers use to measure distances to increasingly remote objects. The foundation of this ladder consists of parallax measurements. As Earth orbits the Sun, nearby stars appear to shift slightly against the background of more distant stars. By measuring this shift, astronomers can calculate the distance to stars within a few thousand light-years of Earth. For greater distances, astronomers use standard candles, objects of known intrinsic brightness. By comparing how bright such an object appears to how bright it actually is, astronomers can calculate its distance using the inverse square law of light. Cepheid variable stars, which pulsate with periods related to their intrinsic luminosity, serve as important standard candles for measuring distances to nearby galaxies. Type 1. Supernovae provide the most powerful standard candles for measuring cosmic distances. These stellar explosions occur when white dwarf stars accumulate too much mass and undergo thermonuclear detonation. The explosions reach remarkably consistent peak brightnesses, allowing astronomers to measure distances to galaxies billions of light-years away. It was observations of distant Type 1a supernova that revealed the accelerating expansion of the universe and the existence of dark energy. Beyond direct distance measurements, astronomers use redshift to gauge cosmic distances. Light from distant galaxies is stretched to longer wavelengths by the expansion of space, shifting it toward the red end of the spectrum. The greater the redshift, the more the light has been stretched, and the greater the distance to the galaxy. The relationship between redshift and distance depends on the cosmological model, allowing astronomers to test theories about the universe's geometry and expansion history. Observations of the cosmic microwave background provide complementary information about the structure of the universe. By analyzing the patterns in this ancient light, scientists can measure the geometry of space, the rate of expansion, and the composition of the cosmos with remarkable precision. These measurements show that the universe is dominated by dark energy at about 68%, dark matter at about 27%, with ordinary matter making up only about 5% of the total. The most distant objects we have observed are galaxies that existed when the universe was only a few 100 million years old. Their light has traveled for over 13 billion years to reach us, crossing most of the observable universe. Beyond these ancient galaxies lies the cosmic microwave background, and beyond that, a wall of opacity where the universe was too hot for light to travel freely. Can we ever see beyond this wall? Not with light. However, scientists are developing new ways to probe the earliest moments of the universe. Gravitational waves, ripples in spacetime caused by violent cosmic events, could carry information about the universe before the cosmic microwave background was released. Neutrinos, ghostly particles that barely interact with matter, could provide another window into the early cosmos. Someday, we might even detect signatures of cosmic inflation imprinted in gravitational waves from the earliest instant after the Big Bang. Such observations could reveal whether inflation happened, how long it lasted, and potentially provide clues about what lies beyond our cosmic horizon. Let us now discuss something called the cosmological principle, an assumption that underlies much of modern cosmology. The cosmological principle states that the universe is homogeneous and isotropic on large scales. Homogeneous means that matter is distributed uniformly throughout space, with no special locations. Isotropic means that the universe looks the same in all directions, with no preferred orientations. On small scales, the universe is clearly not homogeneous or isotropic. Matter clumps into stars, galaxies, and galaxy clusters, with vast voids between them. But on scales of hundreds of millions of light-years, these variations smooth out. The universe becomes like a uniform cosmic foam, with similar patterns of structures wherever we look. The cosmological principle implies that our location in the universe is not special. We do not occupy the center of the cosmos or any other privileged position. Any observer anywhere in the universe would see roughly the same thing we see, a cosmos that appears the same in all directions, with similar structures at similar distances. This principle has important implications for the question of cosmic edges. If the universe has the same properties everywhere, and if our location is not special, then there cannot be an edge somewhere that would make certain locations fundamentally different from others. An edge would create a special location, the place nearest to the boundary, violating the cosmological principle. Of course, the cosmological principle is an assumption that must be tested against observations. So far, it has held up remarkably well. The cosmic microwave background is uniform to 1 part in 100,000 in all directions. Galaxy surveys show similar patterns of clustering throughout the observable universe. But these observations only cover our cosmic neighborhood on the grandest scales. We cannot know for certain whether the cosmological principle holds in regions beyond our horizon. Some cosmologists have proposed variations of the cosmological principle. The perfect cosmological principle, now largely abandoned, stated that the universe is not only uniform in space, but also in time. This principle was the foundation of the steady-state theory, which held that the universe has no beginning or end, with new matter continuously created to maintain constant density as space expands. The discovery of the cosmic microwave background effectively disproved this theory, establishing the Big Bang model that dominates cosmology today. The observable universe provides strong evidence for the Big Bang. The cosmic microwave background is the afterglow of the primordial fireball. The abundance of light elements like hydrogen, helium, and lithium matches predictions from Big Bang nucleosynthesis. The expansion of the universe, when traced backward in time, points to an initial moment of extreme density and temperature. But does the Big Bang represent the beginning of everything? Did the universe emerge from nothing at that moment? Or did something exist before, perhaps another phase of cosmic history that gave rise to the Big Bang? These questions push us to the limits of known physics and beyond. The Big Bang was not an explosion in space, but an expansion of space itself. At the earliest moments, the entire observable universe was concentrated in an incredibly tiny region, perhaps smaller than an atom. Space, time, matter, and energy were all compressed into this point of nearly infinite density. Then, expansion began, and the universe has been growing and cooling ever since. But asking what happened before the Big Bang may be a meaningless question. If time itself began with the Big Bang, then there was no before. Asking what came before would be like asking what is north of the North Pole. The question assumes a reference frame that does not exist. Some theories suggest that time did not begin with the Big Bang. In loop quantum cosmology, the Big Bang was actually a big bounce, where a previous contracting universe collapsed to a minimum size before rebounding into expansion. In this picture, time extends infinitely into the past, with an endless cycle of universal expansion and contraction. The cyclic model proposes that our universe periodically cycles through periods of expansion and contraction, with each Big Bang representing a new cosmic chapter. The ekpyrotic scenario, derived from string theory, suggests that the Big Bang resulted from the collision of higher dimensional membranes in a larger multiverse. Each collision would create a new universe, with its own Big Bang marking the start of a new expansion phase. These theories remain speculative, but they illustrate how the question of cosmic origins connects to the question of cosmic edges. If the universe emerged from a previous state, that previous state might have had different properties, different boundaries, or no boundaries at all. The edge of our universe might be a temporal rather than spatial boundary, separating us from earlier or later phases of cosmic existence. Let us now consider the far future of the universe and what it means for cosmic boundaries. If current theories are correct, the universe faces a long, cold fate, stretching into eternity. Understanding this future helps us appreciate the evolving nature of cosmic horizons and edges. In the near future, cosmically speaking, our Milky Way galaxy will merge with the Andromeda galaxy in about 4 to 5 billion years. The collision will be spectacular, with the two galaxies swirling together over hundreds of millions of years, eventually forming a single giant elliptical galaxy, sometimes called Milkdromeda or Milkomeda. During this merger, our solar system will likely survive intact, though its position in the resulting galaxy is uncertain. The sun will still be burning, though approaching the end of its hydrogen-fusing life. In about 5 billion years, the Sun will swell into a red giant, engulfing Mercury and Venus and rendering Earth uninhabitable. Eventually, the Sun will shed its outer layers and collapse into a white dwarf, slowly cooling over trillions of years. On longer timescales, the expansion of the universe will isolate our local group of galaxies from the rest of the cosmos. Galaxies beyond our local group will accelerate away, eventually crossing our cosmic horizon and disappearing from view forever. In about 100 billion years, the observable universe will contain only our local group, merged into a single giant galaxy, floating alone in an apparently infinite void. The last stars will burn out in about 100 trillion years as the universe exhausts its supply of hydrogen for fusion. After this era of starlight ends, the universe will enter an age of darkness. The only remaining stellar objects will be slowly cooling white dwarfs, neutron stars, and black holes. Black holes themselves will eventually evaporate through Hawking radiation, a quantum mechanical process that causes them to slowly lose mass and energy. The largest supermassive black holes will take around 10 to the 100th power years to evaporate, a number so large it defies comprehension. 1 followed by 100 zeros represents more years than there are atoms in the observable universe, more than all the moments that will ever exist in any recognizable sense. After the black holes are gone, the universe will consist mainly of widely scattered elementary particles, primarily photons, neutrinos, and possibly long-lived particles like protons. These particles will exist at temperatures approaching absolute zero, moving through ever larger volumes of empty space. If protons are stable, they will eventually dominate the matter content of the universe. If protons decay, as some theories suggest, matter itself will eventually dissolve into radiation. Either way, the universe will approach a state of maximum entropy, a uniform sea of lowest energy particles spread through infinite space. This heat death represents an asymptotic approach to absolute zero, though true absolute zero can never be reached. The universe will continue to expand forever, each region becoming increasingly isolated from every other. The cosmic horizon will shrink to encompass less and less, until perhaps only the immediate region of any given observer remains accessible. In this far future, the question of cosmic edges takes on a new meaning. There may be no physical edge to the universe, but the practical horizon will have shrunk to almost nothing. Every region of space will be effectively cut off from every other, trapped in its own private cosmic bubble. The boundless universe will have become, for any observer, effectively finite and utterly alone. Let us shift our focus now to consider how different cultures and civilizations have thought about the boundaries of existence. Throughout human history, people have grappled with questions about what lies at the edge of everything, and their answers reveal much about human imagination and the universal desire to understand our place in the cosmos. Ancient Mesopotamian cultures imagined the universe as a dome, covering a flat earth with waters above and below. The sky was a solid firmament holding back the celestial waters, with gates through which the sun, moon, and stars could pass. In this picture, the universe had definite edges, a dome above and an abyss below, beyond which lay primordial chaos. The ancient Greeks developed more sophisticated cosmologies. Aristotle proposed a finite universe with Earth at the center, surrounded by nested crystalline spheres carrying the moon, sun, planets, and fixed stars. Beyond the sphere of the stars lay nothing, not even empty space. The universe simply ended there, complete and perfect. Epicurus and his followers proposed a radically different view. They argued that the universe was infinite, filled with countless worlds, scattered through boundless void. They reasoned that a finite universe would have a center and an edge, but there is no reason why the center should be where we are, rather than somewhere else. Therefore, every location must be equivalent, which requires an infinite universe with no special places. Medieval Christian cosmology largely followed Aristotle, placing the celestial spheres around a central Earth, with the empyrean, the dwelling place of God, beyond the outermost sphere. This created a bounded universe with theological edges, where physical reality gave way to divine realms. The Copernican revolution displaced Earth from the cosmic center, eventually leading to the realization that the Sun was just one star among many. As telescopes revealed the true scale of the cosmos, the old picture of nested spheres gave way to vast interstellar distances. The universe seemed to extend forever into the depths of space. Hindu cosmology offers perhaps the grandest vision of cosmic scales. In Hindu tradition, the universe goes through endless cycles of creation, preservation, and destruction, each cycle lasting billions of years. The cosmos contains countless world systems, each with its own inhabitants, all arising and dissolving in the eternal dance of existence. There is no ultimate beginning or end, no absolute edge, just endless cycles in infinite space. Buddhist cosmology similarly embraces vast spatial and temporal scales. The universe contains countless world systems grouped into larger structures, with beings in various realms of existence. The cosmos has no creator and no ultimate boundary, extending infinitely in space and time. This vision remarkably anticipates modern scientific ideas about an unbounded universe without edges. Indigenous cultures around the world have their own cosmologies, often reflecting local geography and experience. Many Native American traditions describe layered worlds, with the visible world sandwiched between sky realms above and underground realms below. These cosmologies emphasize connection and relationship rather than boundaries and edges, seeing the universe as a web of interconnected beings rather than a container with walls. The history of human thought about cosmic boundaries reveals a consistent pattern. Early cosmologies tended to be finite and bounded, reflecting the limited scope of direct experience. As knowledge grew, so did conceptions of the universe, from the celestial spheres of antiquity to the infinite cosmos of modern science. At each stage, what seemed like an edge turned out to be merely a horizon with vaster realms beyond. This pattern suggests humility about our current understanding. Modern cosmology has pushed the known universe to unimaginable scales, but we may still be seeing only a fraction of what exists. The observable universe could be a tiny bubble in a vastly larger reality, just as the visible sky turned out to be a tiny neighborhood in a galaxy of billions of stars, which itself turned out to be one galaxy among trillions. Let us now explore some of the philosophical puzzles that arise when we contemplate infinite space. The concept of infinity has fascinated and troubled thinkers throughout history, and its application to the universe raises profound questions. If the universe is truly infinite, then every possible arrangement of matter must occur somewhere. This is because there are only finitely many ways to arrange a finite number of particles, but infinitely many regions of space to fill. Somewhere in an infinite universe, there must be another Earth, another you, reading these same words. In fact, there must be infinitely many such copies, scattered through the boundless void. This conclusion seems absurd, yet it follows logically from the assumption of infinite space and uniform distribution of matter. Some cosmologists embrace this implication, seeing it as a natural consequence of cosmic infinity. Others argue that it reveals a flaw in our assumptions, perhaps indicating that the universe is finite after all, or that matter is not distributed uniformly on the largest scales. The German mathematician David Hilbert famously explored the paradoxes of infinity through his thought experiment of Hilbert's hotel. Imagine a hotel with infinitely many rooms, all occupied. A new guest arrives. In an ordinary hotel, there would be no vacancy. But in Hilbert's hotel, the manager simply asks each guest to move to the next room. The guest in room 1 moves to room 2. The guest in room 2 moves to room 3, and so on. Room 1 is now vacant for the new guest. Infinity plus 1 still equals infinity, but it gets stranger. Suppose infinitely many new guests arrive. The manager asks each current guest to move to the room with twice their current room number. Guest in room 1 moves to room 2. Guest in room 2 moves to room 4. Guest in room 3 moves to room 6. Now all odd-numbered rooms are vacant, infinitely many of them, ready for the infinite new arrivals. These paradoxes illustrate the strange properties of infinite sets, where part of the whole can equal the whole. Applied to an infinite universe, they suggest that adding or removing matter would not change the total amount. The universe could contain the same infinity of galaxies, whether we add 1 trillion more or remove half of them. Some philosophers argue that actual infinities cannot exist in the physical world, only potential infinities. A potential infinity is a process that could continue indefinitely, but never actually reaches infinity. The universe could expand forever, approaching but never achieving infinite size. In this view, there is no infinite universe, only an unbounded one that keeps getting larger without limit. Others argue that actual infinities are not only possible, but necessary. Certain interpretations of quantum mechanics require infinite dimensional mathematical spaces. Some theories of consciousness propose that subjective experience involves infinite information. Whether the physical universe embodies actual or merely potential infinity remains an open question. The German philosopher Immanuel Kant argued that human reason confronts inevitable contradictions when it tries to determine whether the universe is finite or infinite in space and time. He called these contradictions antinomies, paired arguments that seem equally valid but reach opposite conclusions. For Kant, these antinomies revealed the limits of pure reason and the need for a different approach to metaphysical questions. Modern cosmology has largely resolved Kant's spatial antinomy through the concept of curved space. A universe can be finite in volume, yet unbounded, like the surface of a sphere extended to higher dimensions. This allows us to escape the dilemma of choosing between an edge to space and infinite extension. Space can curve back on itself, creating a finite cosmos without boundaries. Whether the temporal antinomy has been similarly resolved is less clear. Did time have a beginning, or does it extend infinitely into the past? The Big Bang seems to mark a beginning, but theories of cosmic cycles or eternal inflation suggest that time might extend beyond it. The question of temporal infinity remains as puzzling as ever. Let us now discuss the role of mathematics in understanding cosmic structure and boundaries. Mathematics has proven remarkably effective in describing the physical universe, from the trajectories of planets to the behavior of atoms. This effectiveness is itself a mystery, as noted by the physicist Eugene Wigner in his famous essay on the unreasonable effectiveness of mathematics in the natural sciences. Einstein's general theory of relativity describes gravity as the curvature of spacetime caused by mass and energy. The equations of general relativity relate the distribution of matter to the geometry of space, allowing scientists to calculate how the universe evolves over time. These equations predicted the expansion of the universe before it was observed, and they correctly describe the behavior of black holes and gravitational waves. Applied to the universe as a whole, general relativity allows different solutions depending on the distribution of matter and energy. Some solutions describe finite universes that eventually recollapse. Others describe infinite universes that expand forever. Still others describe universes with complex topologies, wrapped around themselves in various configurations. The actual geometry of our universe must be determined by observation, not mathematics alone. Quantum mechanics adds another layer of mathematical description. The equations of quantum theory describe the behavior of matter and energy at the smallest scales, predicting phenomena like particle entanglement, superposition, and tunneling. Quantum effects become important at extremely high energies, such as those present in the early universe. Combining quantum mechanics with general relativity has proven extraordinarily difficult. The two theories are individually successful, but fundamentally incompatible in their current forms. At the moment of the Big Bang, when the entire universe was compressed to quantum scales, both theories should apply, but their combination produces nonsensical, infinite results. This failure suggests that our current theories are incomplete. A theory of quantum gravity, combining the insights of both frameworks, remains the holy grail of theoretical physics. String theory, loop quantum gravity, and other approaches attempt to provide such a unified description, but none has yet been confirmed by observation. A successful theory of quantum gravity might revolutionize our understanding of cosmic boundaries. It could reveal whether the Big Bang was truly the beginning of time or a transition from a previous state. It could clarify whether space is continuous or discrete at the smallest scales. It might even determine whether the universe has edges in dimensions beyond our perception. Let us now turn to one of the strangest ideas in modern physics, the holographic principle. This principle, derived from studies of black holes, suggests that the information content of a three-dimensional region of space can be encoded on its two-dimensional boundary. Applied to the entire universe, this principle implies that all of reality might be a kind of hologram projected from a distant cosmic surface. The holographic principle arose from attempts to understand the thermodynamics of black holes. When matter falls into a black hole, information about it seems to disappear, violating fundamental principles of physics. The resolution proposed by Gerard de Hooft and Leonard Susskind in the 1990s is that the information is not lost but encoded on the black hole's event horizon, the boundary from which nothing can escape. If this encoding is possible for black holes, it might be possible for any region of space. The maximum information content of any volume would be proportional not to the volume itself, but to the area of its boundary. This seems counterintuitive, as we normally think of information being stored throughout a volume. But the holographic principle suggests that bulk information is redundant, with all essential data captured on the boundary. Applied to cosmology, the holographic principle suggests that our entire universe might be a projection from a distant boundary. The boundary could be the surface of an enormous cosmic sphere, perhaps at the edge of our observable universe or beyond. All the events, objects, and experiences we know would be encoded on this boundary, with the three-dimensional world we perceive being a kind of elaborate illusion. This idea has been given mathematical precision in a specific example called the ADS/CFT correspondence, discovered by the physicist Juan Maldacena in 1997. This correspondence establishes an exact equivalence between a theory of gravity in a five-dimensional space, called anti-de Sitter space, and a quantum field theory living on the four-dimensional boundary of that space. What happens in the bulk of the space is completely encoded in the boundary theory, and vice versa. Our universe is not anti-de Sitter space. It has positive dark energy and is approximately flat, quite different from the negatively curved geometry of anti-de Sitter space. Whether a holographic description exists for our actual cosmos remains an open question. but the success of the ADS/CFT correspondence suggests that holography might be a general feature of nature, with profound implications for the concept of cosmic boundaries. If the universe is holographic, then the boundary might be the most fundamental reality, with the bulk interior being derivative. The edge of the universe would not be where space ends, but where the true reality lives, projecting the illusion of three-dimensional space into our experience. Let us now consider the anthropic principle and its implications for cosmic structure. The anthropic principle notes that the universe we observe must be compatible with the existence of observers like us. This seemingly obvious statement has surprisingly powerful implications for understanding the properties of the cosmos. The universe seems remarkably fine-tuned for the existence of complex structures like stars, planets, and life. The strength of gravity, the masses of elementary particles, the strengths of nuclear forces, and many other parameters fall within narrow ranges that allow complexity to emerge. If any of these parameters were slightly different, the universe might be sterile, filled only with radiation, or collapsed into black holes. Some see this fine-tuning as evidence of design, a universe created with life in mind. Others argue that it is explained by the multiverse. If countless universes exist with different parameters, we naturally find ourselves in one where conditions permit our existence. There is no need for design, only the vast statistical landscape of possible cosmoses. The anthropic principle has implications for cosmic boundaries as well. If the universe has an edge, observers near the edge might have very different experiences from those in the center. They might see different patterns of galaxies, different cosmic backgrounds, different physical laws, if such variations are possible. The fact that we observe uniform conditions in all directions suggests either that we are far from any edge, or that no edge exists. Strong versions of the anthropic principle go further, suggesting that the existence of observers is somehow necessary for the universe to exist at all. Quantum mechanics seems to require observation to collapse possibilities into definite realities. Perhaps the universe needs observers to actualize itself, creating a cosmic feedback loop where existence and awareness are interdependent. These ideas remain highly speculative and controversial. Many physicists reject the anthropic principle as unscientific or circular. Others embrace it as a useful tool for understanding cosmic selection effects. The debate continues, touching on fundamental questions about the nature of existence and the role of consciousness in the physical world. Let us now discuss cosmic topology, the study of how the universe is connected. Topology is the branch of mathematics concerned with properties that remain unchanged under continuous deformations. A donut and a coffee cup are topologically equivalent because one can be smoothly transformed into the other. A donut and a sphere are topologically different because no smooth transformation can change one into the other without cutting or tearing. The universe might have non-trivial topology, being connected to itself in complex ways. The simplest possibility is that space is infinite and simply connected, stretching forever in all directions without looping back. But more exotic possibilities exist, with space connecting to itself through portals or passages invisible to direct observation. A toroidal universe would wrap around in all three dimensions, like a three-dimensional version of a video game screen. If you traveled far enough in any direction, you would return to your starting point. The universe would be finite in volume, but without any edges or boundaries. Light could circumnavigate the cosmos, potentially allowing us to see the same objects multiple times from different directions. Even more complex topologies are possible. The Poincaré dodecahedral space consists of a dodecahedron, a 12-sided solid, with opposite faces identified. Light, leaving one face, enters through the opposite face, creating a finite but unbounded cosmos with the symmetry of the icosahedron. Scientists have searched for evidence of this topology in the cosmic microwave background, looking for matching patterns that would indicate the finite size of such a space. More exotic still are spaces with multiple connections, where distant regions of the universe are linked by topological passages. Wormholes in general relativity provide one example, connecting separate points in spacetime through tunnels shorter than the normal path through space. While wormholes remain theoretical, their possibility illustrates how cosmic topology could have surprises hidden beyond our observational horizon. So far, no evidence for non-trivial cosmic topology has been found. The cosmic microwave background appears uniform, without the matched patterns expected from a finite wrapped space. This suggests that if the universe has non-trivial topology, it does so on scales larger than the observable universe, where we cannot yet detect its effects. Let us continue our journey with a discussion of dark matter and its implications for cosmic structure. Dark matter is invisible material that exerts gravitational attraction without emitting or absorbing light. It constitutes about 27% of the universe by mass, roughly 5 times as much as ordinary matter. Evidence for dark matter comes from multiple sources. Galaxies rotate faster than they should based on their visible mass alone, suggesting invisible material in their halos. Galaxy clusters remain bound together, despite their galaxies moving too fast to be held by visible gravity. The cosmic microwave background shows patterns consistent with dark matter's gravitational influence in the early universe. Gravitational lensing, where massive objects bend light from more distant sources, reveals invisible mass in galaxies and clusters. Despite abundant evidence for its existence, dark matter has never been directly detected. Numerous experiments search for dark matter particles interacting with ordinary matter, but none has yet succeeded. The nature of dark matter remains one of the great mysteries of modern physics. The leading candidates for dark matter are hypothetical particles called weakly interacting massive particles, or WIMPs. These would be heavy, stable, and interact only through gravity, and possibly the weak nuclear force. Other candidates include axions, hypothetical light particles that could constitute cold dark matter, and primordial black holes, formed in the early universe before ordinary matter existed. Dark matter affects cosmic structure in profound ways. In the early universe, dark matter began clumping under gravity before ordinary matter could. These dark matter clumps provided the gravitational wells into which ordinary matter later fell, eventually forming galaxies and galaxy clusters. Without dark matter, the universe might have remained a smooth sea of gas, without the concentrated structures we observe. The distribution of dark matter forms a cosmic web, a vast network of filaments and nodes spanning the universe. Galaxies cluster along these filaments, concentrated at the intersections where dark matter is densest. Vast voids exist between the filaments, nearly empty regions spanning hundreds of millions of light years. This web has no edge that we have detected. It appears to extend throughout the observable universe, and presumably beyond. If the universe is infinite, the dark matter web extends infinitely as well, an endless lattice of filaments and voids, stretching forever in all directions. Let us now explore primordial gravitational waves, ripples in space-time from the earliest moments of cosmic history. These waves could provide our most direct glimpse into what happened at or even before the Big Bang. Gravitational waves are distortions in the fabric of space-time, caused by accelerating masses. Einstein predicted their existence in 1916, but they were not directly detected until 2016 by the Laser Interferometer Gravitational Wave Observatory or LIGO. That detection confirmed waves from merging black holes, opening a new window on the cosmos. The early universe may have produced gravitational waves through various mechanisms. During cosmic inflation, quantum fluctuations in spacetime would have been stretched to cosmic scales, creating a background of primordial gravitational waves permeating all of space. The specific pattern of these waves would encode information about inflation's energy scale and duration. Even more dramatically, gravitational waves might carry information from before the Big Bang. In cyclic models of the universe, each Big Bang produces gravitational waves that could persist through the cycle into the next cosmic era. Detecting such pre-Big Bang signals would revolutionize our understanding of cosmic origins. Scientists are searching for primordial gravitational waves through their effects on the cosmic microwave background. Gravitational waves would have imprinted a distinctive swirling pattern called B-mode polarization on the ancient light. The BICEP experiment reported detection of this signal in 2014, but subsequent analysis showed it was likely due to cosmic dust rather than gravitational waves. Future experiments will continue the search with improved sensitivity. Space-based detectors could observe gravitational waves directly, free from the vibrations that plague ground-based instruments. If primordial gravitational waves are detected, they would provide information about cosmic conditions at energies far beyond what particle accelerators can achieve. These waves might also reveal something about cosmic boundaries. The spectrum and distribution of primordial gravitational waves would depend on the topology and curvature of space at the earliest moments. Certain patterns would indicate a finite universe, while others would favor infinite extension. Gravitational waves offer a potential probe of cosmic structure beyond the visible horizon. Let us now discuss cosmic nucleosynthesis, the formation of the lightest elements in the first minutes after the Big Bang. This process created the hydrogen, helium, and lithium that form the foundation of cosmic chemistry, and its predictions provide some of the strongest evidence for the Big Bang model. In the first second after the Big Bang, the universe was too hot for atomic nuclei to exist. Protons and neutrons existed in a sea of radiation, constantly being created and destroyed. As the universe expanded and cooled, these particles began combining into light nuclei. About 3 minutes after the Big Bang, the temperature had dropped enough for deuterium, an isotope of hydrogen with 1 proton and 1 neutron, to survive. Deuterium quickly combined into helium-3 and helium-4 with trace amounts of lithium-7. After about 20 minutes, the universe had cooled too much for further nuclear fusion, and nucleosynthesis ended. The Big Bang nucleosynthesis model predicts specific abundances for these light elements. Hydrogen should constitute about 75% of ordinary matter by mass, helium about 24%, and deuterium and lithium 7 tiny fractions. Observations of the oldest stars and most pristine gas clouds in the universe confirm these predictions with remarkable accuracy. This agreement provides strong support for the Big Bang model and constrains cosmological parameters. The amount of ordinary matter in the universe can be calculated from the primordial abundances, yielding about 5% of the total cosmic density. This leaves room for dark matter and dark energy to dominate the cosmic inventory. Big Bang nucleosynthesis also tells us about conditions throughout the observable universe. The uniformity of primordial element abundances suggests that the same physics operated everywhere we can observe. There is no evidence for regions with different nuclear physics or different primordial compositions. This uniformity is consistent with the cosmological principle and argues against any local edges or boundaries in the observable universe. Let us now explore the concept of cosmic horizons in more detail. We have mentioned the observable universe and the cosmic event horizon, but several distinct horizons play important roles in cosmology. The particle horizon represents the maximum distance from which light could have reached us since the beginning of the universe. This defines the boundary of the observable universe, beyond which we cannot see because light has not had time to reach us. The particle horizon expands at the speed of light as the universe ages, bringing more distant regions into view over time. The event horizon represents the distance beyond which events occurring now will never be observable to us. Due to the accelerating expansion of the universe, some regions are receding from us so quickly that their light will never reach us. These regions have crossed our cosmic event horizon and are permanently beyond our ken. The Hubble horizon marks the distance at which the expansion of space causes galaxies to recede from us at the speed of light. This horizon is closer than the particle horizon because space continues to expand as light travels, stretching the distances involved. Objects beyond the Hubble horizon are receding faster than light, though they can still be visible if they were closer in the past when they emitted their light. These horizons are not physical barriers, but observational limits. They define what we can see and know, not where space ends. Beyond every horizon, the universe presumably continues with similar properties, just forever hidden from our view. The interplay of these horizons creates the strange situation of our cosmic neighborhood. We can see ancient light from galaxies that were inside our particle horizon when they emitted it, but have since crossed our event horizon and are now permanently inaccessible. We observe their past, but can never see their present or future. They exist in the universe, but not in our accessible reality. As the universe continues to expand and accelerate, these horizons will change. The event horizon will shrink as more and more galaxies cross beyond it. The accessible universe will contain less and less as cosmic expansion isolates our local group. In the far future, our descendants will inhabit a universe that appears much smaller than ours, with most of cosmic history and structure permanently hidden. Let us now consider a fascinating phenomenon called the cosmic microwave background cold spot. This region of unusually cold temperature in the cosmic microwave background has puzzled scientists since its discovery and may provide clues about cosmic structure beyond the visible horizon. The cold spot was identified in data from the Wilkinson Microwave Anisotropy Probe in 2004. It spans about 5 degrees on the sky, much larger than typical temperature fluctuations in the cosmic microwave background. Its temperature is about 70 millionths of a degree cooler than the average, a significant deviation given the overall uniformity of the background radiation. Several explanations have been proposed for the cold spot. One possibility is that it results from a supervoid, an enormous region of below-average density along our line of sight. Light passing through such a void would lose energy due to the accelerating expansion of space within it, appearing cooler when it reaches us. The Eridanus supervoid, a large empty region roughly 10 billion light-years away, has been proposed as the source. However, calculations suggest that known voids cannot fully explain the cold spot's depth. Alternative explanations invoke more exotic physics. The cold spot might result from the collision of our universe with another universe bubble in a multiverse scenario. Such a collision would leave an imprint on the cosmic microwave background, potentially matching the observed properties of the cold spot. If this explanation is correct, the cold spot would provide evidence for the existence of other universes beyond our own. Our universe would have an edge of sorts, a boundary where it meets or collided with its cosmic neighbor. The cold spot would be a scar from this ancient encounter, visible in the oldest light of our universe. Other explanations attribute the cold spot to statistical fluctuations, instrumental effects, or foreground contamination from our own galaxy. Distinguishing among these possibilities requires further observation and analysis. The cold spot remains a tantalizing hint that the universe may hold surprises beyond our current understanding. Let us now explore the entropy of the universe and its implications for cosmic structure and boundaries. Entropy is a measure of disorder or randomness, and its behavior over cosmic time reveals deep truths about the nature of the universe. The second law of thermodynamics states that the total entropy of an isolated system never decreases. In the universe as a whole, entropy increases over time, driving the arrow of time from past to future. The early universe had remarkably low entropy, and it has been increasing ever since, driving all the changes and processes we observe. But how could the early universe have such low entropy? The hot, uniform plasma of the early cosmos might seem highly disordered, like a well-mixed gas. Yet this state actually had extremely low gravitational entropy. Gravity tends to clump matter together, and a smooth distribution of matter represents a highly ordered configuration gravitationally. As the universe evolved, gravity pulled matter into increasingly clumped structures, galaxies, stars, black holes, increasing gravitational entropy enormously. Black holes, in particular, have incredibly high entropy, with a single stellar mass black hole containing more entropy than all the ordinary matter in the observable universe. The ultimate fate of the universe is maximum entropy, the heat death we discussed earlier. In this state, all gradients and differences have been erased, leaving a uniform sea of particles at equilibrium. No further change is possible because there are no remaining gradients to drive processes. Time continues to pass, but nothing happens. This thermodynamic picture connects to the question of cosmic boundaries. An infinite universe can have infinite entropy, growing forever without limit. A finite universe has finite maximum entropy, though this maximum might never be reached if space continues to expand. The relationship between entropy, information, and cosmic structure remains an active area of research. Some physicists propose that entropy might explain the arrow of time, and even the apparent low entropy beginning of the universe. In eternal inflation scenarios, our low entropy Big Bang might be a rare fluctuation in an otherwise high entropy, eternally inflating multiverse. We find ourselves in a low entropy region because only such regions permit complex observers like us. Let us now discuss the fascinating topic of cosmic strings and other topological defects. These hypothetical structures might exist as relics from the early universe, stretched to cosmic scales by the expansion of space. In the early universe, as it cooled through various phase transitions, different regions of space might have settled into different vacuum states. Where regions with incompatible vacuum states met, energy would be trapped in the boundary between them, creating defects in the fabric of space. Cosmic strings are one-dimensional defects, infinitesimally thin, but potentially stretching across the universe. They would be incredibly dense, with a single centimeter of cosmic string weighing as much as a mountain. Moving through space, cosmic strings would bend light from more distant sources, creating distinctive doubled images of galaxies and quasars. Domain walls are two-dimensional defects, sheets of trapped energy separating regions of different vacuum states. If domain walls existed in significant numbers, their gravitational effects would dominate the universe, conflicting with observations. This suggests that if domain walls formed, they were unstable and quickly disappeared. Monopoles are zero-dimensional defects, point-like concentrations of magnetic charge. Grand unified theories predict that monopoles should have formed abundantly in the early universe, yet none have ever been observed. This monopole problem was one of the motivations for cosmic inflation, which would have diluted any primordial monopoles to undetectable levels. Cosmic strings, if they exist, could provide evidence about the topology of vacuum states in fundamental physics. Observational searches for cosmic strings continue, looking for their gravitational effects on the cosmic microwave background and distant light sources. So far, no convincing evidence for cosmic strings has been found, but their existence remains possible within current observational constraints. These topological defects relate to cosmic boundaries in an interesting way. They represent edges or walls within the universe, boundaries between regions with different vacuum properties. While not edges of the universe itself, they would be edges of a sort, marking transitions between distinct cosmic domains. Let us now explore the possibility that the universe might have different properties in distant regions, variations in fundamental constants or physical laws that would create effective boundaries without actual walls. The fine structure constant determines the strength of electromagnetic interactions and affects atomic structure, chemistry, and the properties of matter. If this constant had different values in different regions of the universe, matter would behave differently there. Atoms might be larger or smaller, chemical reactions faster or slower, stars hotter or cooler. Observations of distant quasars have been used to search for variations in the fine structure constant over cosmic time and space. Some studies have reported hints of variation, with the constant appearing slightly different in different directions on the sky. However, these results remain controversial, with other studies finding no evidence for variation. If fundamental constants vary across the universe, the regions where our values apply would constitute our effective cosmic home. Crossing into regions with different constants would be like entering a different universe, with matter and energy behaving according to unfamiliar rules. These variations would create boundaries without walls, edges without surfaces. The string theory landscape provides a framework for understanding such variations. In string theory, the vacuum state of spacetime can take many different forms, each with different effective physical laws. The multiverse might consist of regions with all possible vacuum states, separated by transitions where constants change. Such a picture would mean that our universe has edges of a sort, boundaries beyond which our physics no longer applies. We might never be able to cross these boundaries, or even detect them if they lie beyond our cosmic horizon, but they would represent the true limits of our cosmic domain, the edge of the region where we and everything we know can exist. Let us now discuss the remarkable uniformity of the cosmic microwave background and what it tells us about cosmic boundaries. The microwave background is uniform to 1 part in 100,000 across the entire sky, an almost perfect isotropy that poses deep puzzles for cosmology. When we observe the cosmic microwave background in opposite directions, we are seeing regions of space that were never in causal contact with each other. Light from one side of the sky has been traveling toward us for most of cosmic history, as has light from the opposite side. These regions never had a chance to exchange information or reach thermal equilibrium, yet they have the same temperature to extraordinary precision. This horizon problem was one of the main motivations for cosmic inflation. If the early universe underwent a period of exponential expansion, regions that are now widely separated would have been in contact before inflation began. They could have reached equilibrium then, explaining the uniform temperature we observe today. Inflation also explains why the universe is so flat. Any initial curvature would have been diluted by the enormous expansion, leaving the universe effectively flat. This prediction has been confirmed by observations of the cosmic microwave background, which show the universe to be flat to within measurement precision. The tiny fluctuations in the cosmic microwave background, the 1 part in 100,000 variations, are equally important. These fluctuations originated as quantum fluctuations in the inflaton field, the hypothetical field driving inflation. Stretched to cosmic scales by expansion, they seeded the density variations that eventually grew into galaxies and large-scale structure. The pattern of these fluctuations contains information about cosmic geometry and boundaries. If the universe were finite and wrapped around itself, we would expect to see matching patterns at different points in the sky. If the universe had an edge, we might see asymmetries or gradients indicating our position relative to that edge. The observed patterns are consistent with an infinite or very large universe without detectable boundaries. Let us now explore what happens at the boundary of black holes and how this relates to cosmic boundaries. Black holes are regions where gravity has become so intense that nothing, not even light, can escape. They represent edges within the universe, points of no return for anything that crosses them. The event horizon of a black hole marks this boundary. It is not a physical surface, but a mathematical boundary, the point where the escape velocity equals the speed of light. Anything crossing the event horizon is doomed to fall toward the central singularity, unable to communicate with the outside universe. Black hole singularities represent the limits of known physics. At the singularity, density and curvature become infinite, and our equations break down. The singularity might be a point where spacetime ends, an edge of reality within the cosmic fabric. Or it might be a gateway to other regions, as some theories of wormholes suggest. The information paradox of black holes connects to questions about cosmic boundaries. When matter falls into a black hole, information about it seems to disappear. Yet quantum mechanics demands that information be conserved. This paradox has led to ideas like the holographic principle, where information is encoded on the event horizon rather than being destroyed. If black holes preserve information holographically, their event horizons are not simply edges, but storage surfaces. The interior of the black hole might be a kind of illusion, projected from the boundary, just as the holographic principle suggests the entire universe might be projected from a cosmic boundary. Recent work on black hole physics has revealed surprising connections to quantum information theory. The entanglement between particles inside and outside the horizon creates subtle correlations that might allow information to escape over very long timescales. These developments suggest that what happens at black hole boundaries might teach us about cosmic boundaries as well. Let us now consider the question of what existed before the Big Bang, and whether this question even makes sense. If time began with the Big Bang, then there was no before, and the question is meaningless. But several theoretical frameworks suggest that something might have preceded our cosmic beginning. Loop quantum cosmology provides one picture of a pre-Big Bang era. In this theory, space and time are quantized, existing in discrete units rather than continuous values. The Big Bang singularity is replaced by a big bounce, where a previous contracting universe reached a minimum size before rebounding into expansion. Time extends infinitely into the past, with our universe emerging from the ashes of its predecessor. The ekpyrotic scenario imagines our universe as a membrane floating in a higher dimensional space. Another membrane exists parallel to ours, separated by a higher dimensional gap. Occasionally, these membranes collide, releasing enormous energy that appears as a big bang to observers on each membrane. Our universe might have experienced many such big bangs, separated by long periods of expansion and contraction. Conformal cyclic cosmology, proposed by the physicist Roger Penrose, suggests that the universe goes through infinite cycles of expansion. Each cycle ends in a heat death, a uniform state of maximum entropy. But this endpoint is mathematically identical to the smooth, low-entropy beginning of a new cycle. The end of one universe becomes the beginning of the next, in an endless sequence of cosmic eras. These theories suggest that the Big Bang was not the absolute beginning, but a transition from a previous state. Our universe might have boundaries in time, moments of beginning and ending, but these boundaries connect to other epochs rather than nothingness. The edge of our universe would be the interface with what came before, or what comes after. Let us reflect now on what we have learned about the edge of the universe. The observable universe has definite boundaries, horizons beyond which we cannot see. But these horizons are not walls or barriers, just limits of our perception, created by the finite speed of light and the finite age of the cosmos. Beyond the observable universe, space almost certainly continues. How far it extends remains unknown. It might extend infinitely, a boundless expanse without any edge. It might wrap around on itself, finite in volume but without boundaries. It might be one bubble in a vast multiverse, with edges that separate us from other cosmic domains with different properties. The question of cosmic edges connects to the deepest mysteries in physics and philosophy. What is the nature of space? Did it have a beginning? Will it have an end? Is our universe all that exists? Or is it just one island in an infinite cosmic sea? These questions have occupied human thought for millennia and continue to inspire scientific research today. Modern cosmology has revealed a universe far stranger and more magnificent than earlier thinkers could have imagined. The cosmos is not static, but evolving, expanding from a hot, dense beginning toward a cold, dark future. It is filled not just with visible matter, but with dark matter and dark energy, invisible components that dominate its structure and fate. The universe might have more than 3 spatial dimensions, with extra dimensions curled up at scales too small to detect. It might be a hologram, projected from a distant boundary. It might be one of countless universes in an eternal multiverse. These possibilities, once the realm of science fiction, are now serious subjects of scientific research. As we contemplate these cosmic mysteries, a sense of humility is appropriate. The universe far exceeds our ability to comprehend it fully. Every answer raises new questions. Every horizon, once reached, reveals new horizons beyond. The edge of the universe, if it exists, remains forever at the edge of our understanding. And yet, the quest to understand continues. Each generation builds on the knowledge of its predecessors, pushing the boundaries of what is known. The telescopes of tomorrow will see farther than those of today. New theories will illuminate mysteries that currently baffle us. The edge of the universe, whatever its nature, calls to us, inviting exploration and wonder. The cosmos is our home, the vast arena in which our tiny species plays its part. Whether the universe has an edge or extends forever, we are part of it, made from its matter, bound by its laws, participants in its grand unfolding. The atoms in our bodies were forged in the cores of ancient stars. The calcium in our bones, the iron in our blood, the carbon in our cells all have cosmic origins stretching back billions of years. We are the universe contemplating itself, the cosmos awakening to its own existence through our minds. When we ask whether the universe has an edge, we are part of the universe asking about itself. This remarkable recursion, consciousness emerging from matter and turning to investigate its source, is perhaps the deepest mystery of all. The night sky that earlier humans gazed upon with wonder remains our window to the cosmos. The same stars and galaxies that prompted ancient questions about cosmic boundaries still shine above us, still beckoning us to explore. Our tools have become more powerful, our theories more sophisticated, but the fundamental wonder remains unchanged. Whether drifting off to sleep under the actual stars or simply imagining them, we can take comfort in our connection to this vast cosmic tapestry. We are small, yes, impossibly small compared to the universe, but we are also participants in something magnificent. children of the cosmos exploring our cosmic home. The edge of the universe may always recede before us, like the horizon on an endless ocean. But the journey of exploration is its own reward. Each discovery enriches our understanding and deepens our appreciation of the cosmos we inhabit. The universe may be infinite, but so, in its own way, is the human capacity for wonder. As the mind relaxes and consciousness fades toward sleep, the questions about cosmic edges can settle into peaceful contemplation. The universe continues its expansion, whether we are awake or asleep, aware or unaware. Stars continue to shine, galaxies continue their stately rotations, and the cosmic microwave background continues its ancient journey across space. In dreams, perhaps, we can imagine traveling to the edge of the universe, approaching horizons that recede forever before us. We can envision what it might be like to witness the Big Bang or the heat death, to see the cosmic web from outside, to understand at last the true nature of space and time. And when morning comes, the questions will still be there, the mysteries still beckoning. The edge of the universe remains to be found or proven non-existent. The quest continues, passed from generation to generation, an endless exploration of our endless home. The universe is full of questions we may never answer. Does it have an edge? What lies beyond? Did it have a beginning? Will it have an end? These questions humble us, even as they inspire us. They remind us how much remains to be discovered, how much mystery still surrounds our existence. But there is comfort in the mystery. A universe we could fully understand might be a universe too small for our spirits. The fact that questions remain, that horizons beckon, that edges elude us, means there is always more to explore, more to learn, more to wonder at. As sleep approaches and thoughts grow hazy, the edge of the universe can become a gentle companion rather than an urgent question. It is out there somewhere, or perhaps nowhere. It is beyond our reach, but not beyond our dreams. It waits for future generations with better tools and deeper understanding, or it recedes forever, maintaining its mystery. The cosmos wraps around us like a blanket of stars, warm with the ancient light of distant suns. Somewhere in that immensity, an edge may wait to be discovered, or the cosmos may extend forever, infinite and unbounded, a universe without walls. Either way, we are part of it. We belong here, in this vast, mysterious, beautiful universe. Our questions are part of its unfolding, our wonder part of its wonder at itself. The edge of the universe, whether it exists or not, is ultimately just another face of the infinite mystery we call home, and so we drift toward sleep, cradled by gravity, warmed by starlight, surrounded by the endlessly fascinating cosmos. The questions can wait until morning. The universe will still be there, still mysterious, still magnificent, still beckoning us toward horizons forever just beyond reach. The night is long, but the universe is longer still. Stars will shine and galaxies will turn while we sleep, oblivious to the cosmic dance continuing around us. When we wake, the universe will be waiting, ready to inspire new questions, new wonder, new dreams of edges and horizons. For now, let the questions rest. Let the mystery be a comfort rather than a burden. The edge of the universe, wherever it is or is not, cannot be reached tonight. But it can be contemplated, wondered at, and dreamed about as consciousness fades and sleep approaches. The cosmos is vast beyond measure, ancient beyond comprehension, mysterious beyond our ability to fully grasp. And we are part of it, brief sparks of awareness in an immense darkness, asking questions that echo into infinity. The edge of the universe may forever elude us, but the asking of the question connects us to everything that exists. Sleep well, fellow traveler through the cosmos. The universe continues its eternal dance while you rest. Tomorrow brings new opportunities to wonder, to question, to explore. The edge of the universe will still be there, or not there, waiting for minds curious enough to seek it. For now, let the gentle contemplation of cosmic mysteries ease the mind toward rest. The stars shine, the galaxies turn, the universe expands. And somewhere, perhaps, an edge awaits discovery. Or perhaps the cosmos extends forever, infinite and whole, encompassing all possibilities in its eternal embrace. The mystery is beautiful. The questions are gifts. The universe is home. Rest now, and dream of edges and infinities, of horizons and boundaries, of all that exists and all that might exist beyond the limits of our knowledge. The cosmos holds us gently as we sleep, spinning through space around our star, which orbits through our galaxy, which flows through the cosmic web toward destinations unknown. We are small, but we are connected to everything. We are brief, but we are part of the eternal. The edge of the universe, if it exists, is part of us too. We carry the cosmos within us, its questions and mysteries woven into our being. When we wonder about cosmic boundaries, we are the universe wondering about itself. And so the circle closes. The universe contains us, and we contain the universe. The edge of the cosmos, if there is one, exists within us as surely as it exists out there among the distant galaxies. We are the universe experiencing itself, questioning itself, dreaming of its own edges. Sleep approaches now, the daily boundary between waking and dreaming. Beyond this edge lies the country of dreams, where the laws of physics need not apply, where the universe can have any shape we imagine. Perhaps tonight you will dream of cosmic edges, of boundaries and horizons, of what lies beyond the beyond. The universe will keep its secrets while you sleep. It has kept them for billions of years and will keep them for billions more. But it also reveals itself, bit by bit, to those who look and wonder. Tomorrow may bring new discoveries, new insights, new understanding of cosmic structure and boundaries. For now, rest. Let the questions settle like stars coming out at dusk. Let the mysteries hover peacefully at the edge of awareness. The cosmos is patient. The edge of the universe, wherever it is not going anywhere. Dreams await, full of possibility and wonder. The sleeping mind can travel anywhere, even to the edge of the universe, even beyond. In dreams, all boundaries dissolve, all edges become permeable, all questions find answers that the waking mind cannot imagine. Sleep well, and may your dreams carry you to the far reaches of cosmic possibility. The universe is with you, within you, around you, infinite and intimate at once. The edge of everything may be closer than you think, or farther than imagination can reach. Either way, you are home. The cosmos is home. Rest in that knowledge as consciousness fades. The universe loves its children, these brief sparks of awareness that wonder about its edges. It holds us gently as we sleep, spinning through the infinite night. The edge of the universe is a beautiful mystery, a question that enriches our existence, even if it is never fully answered. It reminds us how much remains unknown, how vast the cosmos truly is, how fortunate we are to be here asking such questions at all. And with that thought, let sleep arrive. The questions have been asked, the mysteries have been contemplated, the cosmic journey continues, whether we are awake to witness it or not. The edge of the universe awaits future explorers, future dreamers, future minds wondering about infinity. Rest now. Dream of stars and galaxies, of edges and infinities, of all the beauty and mystery that the universe contains. Tomorrow, the exploration continues. Tonight, let sleep be its own horizon, its own edge to cross, its own territory to explore. The universe is vast, and so are dreams. Both contain multitudes, both harbor mysteries, both offer endless territories for exploration. The edge of the universe and the edge of sleep share a certain kinship, boundaries that beckon and recede, inviting passage into unknown realms. Sleep carries us across its edge every night, into territories our waking minds cannot fully remember or understand. Perhaps death is a similar crossing, into territories our living minds cannot comprehend. And perhaps the edge of the universe is yet another threshold, separating what we know from what lies eternally beyond. All edges are invitations. All boundaries beckon. The cosmos is full of thresholds waiting to be crossed, mysteries waiting to be explored, questions waiting to be asked. The edge of the universe is just one more invitation, one more beckoning horizon, one more reason to wonder. And wondering is a gift. It elevates us above mere existence, connecting us to the cosmos in profound ways. When we wonder about the edge of the universe, we participate in the cosmic drama, playing our small but precious role in the universe's awakening to itself. Sleep now approaches its own edge, the boundary between consciousness and dreams. Cross this threshold gently, carrying your cosmic questions into the realm of sleep. The universe will be waiting when you wake, still mysterious, still magnificent, still inviting exploration. The edge of the universe may never be found, or it may be discovered tomorrow. Either way, the search enriches us, the questions elevate us, the wonder connects us to everything that exists. We are part of the cosmos, and the cosmos is part of us, an intimate connection that transcends all boundaries and edges. Rest in that connection. Sleep in that knowledge. Dream of infinite possibilities and finite moments, of edges and centers, of all that exists and all that might exist. The universe holds you, now and always, part of its eternal unfolding. The questions will keep. The mysteries will remain. The edge of the universe, wherever it is patient. It has waited billions of years and can wait a little longer while you sleep. Tomorrow, the exploration continues. Tonight, let peace settle over wandering like starlight settling over Earth. The cosmos is home. We belong here. The edge of the universe, near or far, real or imaginary, is part of our home too. We carry it within us as we carry the stars within us, cosmic heritage woven into every atom of our being. Sleep well, child of the cosmos. Dream well, citizen of infinity. Rest well, explorer of edges. The universe awaits your return to waking wonder. But for now, let sleep be enough. Let dreams carry the questions while consciousness rests. The edge of the universe is beautiful precisely because it is unknown. It represents all that remains to be discovered, all that still inspires wonder, all that makes existence an adventure rather than a certainty. May that beauty accompany you into sleep, a gentle companion through the territories of dreams, and may you wake refreshed, ready to wonder anew at the magnificent cosmos that is our home. The edge of the universe will still be there, still mysterious, still beckoning. But for now, let it rest while you rest. Let it dream while you dream. Let it wait while you sleep. The journey continues, always and forever, through spaces that may be infinite and times that may be eternal. The edge of the universe is part of that journey, a destination that may never be reached, but that makes the journey worthwhile. Sleep now. The cosmos will keep turning. The questions will keep calling. The edge of the universe will keep its secrets a little longer. And you will wake to wonder again, as humans have wondered since they first looked up at the stars and asked what lay beyond. That wondering is perhaps the most human thing we do. It connects us to our ancestors and our descendants, all those who have gazed at the stars and asked the same eternal questions. The edge of the universe belongs to all of us, a shared mystery that binds humanity together across time and space. And so, with that thought, let sleep arrive. Join the countless humans who have drifted off to sleep, wondering about the cosmos. Become part of that eternal chain of wanderers, dreamers, explorers of the unknown. The edge of the universe awaits us all, patient and mysterious, beautiful and unreachable. Sleep peacefully, wrapped in cosmic mystery. Dream boldly, carried by infinite possibility. Rest deeply, held by the universe that is your home. Tomorrow, the questions return. Tonight, let them rest with you, gentle companions, through the territories of sleep. The edge of the universe is everywhere and nowhere, near and far, real and imagined. It is the limit of our knowledge and the beginning of our wonder. It is where the known becomes unknown and where questions become dreams. Cross that edge now, from waking to sleeping, from wondering to resting. The universe will keep its secrets a little longer. The edge will remain at the edge, beckoning future exploration. And you will return, refreshed and ready to wonder again. Good night, traveler. Good night, wanderer. Good night, cosmic explorer. The universe holds you gently as you sleep, spinning through space toward destinations unknown. Dream of edges and infinities, of boundaries and freedoms, of all that exists and all that waits to be discovered. The cosmos is vast, and so is the human capacity for wonder. Both extend beyond any horizon we can imagine, infinite in their own ways. The edge of the universe and the edge of sleep meet here at this moment, as consciousness fades and dreams begin. Rest now. The cosmos continues its eternal dance. The questions wait, the mysteries remain, and somewhere, perhaps, the edge of the universe shimmers just beyond reach, beautiful in its unreachability, magnificent in its mystery. The night is deep, and so is the cosmos. Both hold secrets we may never fully understand, but understanding is not always necessary. Sometimes simply wondering is enough. Sometimes simply resting in mystery is the greatest gift of all. Sleep well, beloved child of the universe. Dream well, curious spirit exploring infinity. Rest well, weary traveler returning from the edges of thought. Tomorrow brings new horizons, new questions, new opportunities for wonder. Tonight, let sleep be horizon enough. Let dreams be exploration enough. Let rest be wonder enough. The edge of the universe can wait. It has been waiting since the beginning of time, and it will wait a little longer while you sleep. The cosmos embraces you now, as it has always embraced you, as it will always embrace you. You are made of stars, of cosmic dust, of primordial hydrogen transformed through billions of years into the wonder that is you. The edge of the universe is part of you, as you are part of it. Rest in that unity. Sleep in that connection. Dream in that vastness. The questions will return with morning, but for now, let them rest. The mysteries will remain, but for now, let them be peaceful companions rather than urgent demands. The universe is kind to its dreamers. It gives them stars to wonder at, questions to ponder, edges to seek. It gives them sleep to restore them, and dreams to carry them beyond waking limits. It gives them each other, fellow travelers on this cosmic journey. And so the night deepens, and sleep deepens with it. The edge of the universe recedes into peaceful distance, still there, still beckoning, but no longer urgent. The questions settle like stars, settling into their ancient patterns, familiar and comforting. Rest now. Dream now. Sleep now. The universe will still be there when you wake, vast and mysterious and beautiful beyond measure. The edge of the universe will still be there, wherever it is, waiting for minds curious enough to seek it. Tomorrow, the wonder continues. Tonight, let rest be enough. The cosmos spins on, carrying its sleeping children through space and time, toward edges that may never be reached, but are always worth seeking. Sleep well. The universe loves its dreamers.